I'm going to start with a quick review of acids and bases so that we can then move forward and apply our math to these concepts. Your acids are around you in your everyday life, from Coca-Cola to the ammonia you clean with. Coffee is a base. Most of these are organic acids and bases, and we'll learn to recognize those parts of the structure, but they all have the same acidic properties. The properties that we're looking at for acids, and these are pretty basic that you learned even in the 11th grade. They taste sour. They conduct electricity, meaning they're electrolytes. They're either strong or weak electrolytes, depending on the percent that they ionize. They react with most metals to form hydrogen gas. They change indicator colors, and they react with bases to form water and salts. The typical reaction there is acid and base make salt and water, salt being any ionic compound. So you're going to get potassium nitrate in water, magnesium chloride, sodium sulfate, all basic ideas in your beginning chapters on acids and bases. Your neutralization left you with the pH of 7. That will not be the case as we move into more advanced problem solving with weak acids and weak bases. They'll still be neutral, but the salts will be able to affect the pH. Your polyprotic acids are simply acids that have more than one ionizable hydrogen. Again, H2SO4, H3PO4, di- and triprotic acids. You need to recognize that those acid hydrogens are attached to the oxygen in the structure. So the acidic hydrogen is always attached to an oxygen. An organic acid has a structure very different from a mineral acid. You still have an acidic hydrogen, but it comes off of this C double bond O, and there's your acidic hydrogen. We often write the organic acids with hydrogen in the middle. These hydrogens are not acidic. They do not come off of oxygen atoms and therefore are not ionizable. The Arrhenius definition of an acid simply was the first and simplest, that hydrogen ions, or actually, of course, hydronium ions, were produced in aqueous solution, and bases produced hydroxide. But this would limit the definition of acids and bases to only those that would produce those ions. There are weak bases that are going to react with water to later form the hydroxide ion. So we needed to broaden our definition of acids and bases, and we do that with the Bronsted-Lowry definition. An acid is now determined to be a proton, or H plus donor, and a base is a proton acceptor, and they always come in pairs. HCl is an acid because it donates that proton. It's not an organic acid, therefore that hydrogen is not attached to an oxygen. It's only in organic acids that the ionizable hydrogens are attached to oxygens. When it dissociates in water, it gives the hydronium ion and the chloride ion. So the mechanism is that it donates the proton to the water. The water accepts that proton. So the water would be the base, the HCl would be the acid. If you follow that pattern with Bronsted-Lowry, you'll always be able to predict the chemistry that takes place. Again, it is the hydronium ion that's actually formed. We often shorthand it, but it is best to write the complete reaction so that you understand the chemistry and understand all of the species and what is going on. To do this is fine if you truly understand what is going on for that hydrogen ion to be removed. There must be a base, and that base must be water. Sometimes taking these shortcut equations will really hurt you with the math later on. You then need to be able to differentiate between strong acids and weak acids. And strong acids simply dissociate 100%. When you're done, you have no HA left at all. Okay? Your weak acids, okay, have mostly your weak acid and very little percent ionization. Usually less than 1% is in ionized form. So 100% ionized form and certainly less than 1% ionized form. Ka values are not assigned to strong acids. The assumption is that strong acids dissociate 100%, and if your Ka is well above 1, then you're considered strong. Those acids are the typical strong acids that you've always had to memorize: HCl, HBr, HI, nitric sulfuric, and perchloric. Nitric acid has a Ka of 28, HCl and these other acids are thousands to 10 to the 7th power. Some books will list HClO3 as a strong acid, but with a Ka to the -2, it is absolutely not considered a strong acid, even though some books will give that, and some of the problems we'll look at will indicate that it is, but it is not. HClO4 is, and when we look at structures of acids, we'll go more into why it is not able to remove those hydrogens from the oxygens. When you're looking at the strength of an acid, you have to realize that the reaction is reversible. There's an equilibrium between the ionized and the non-ionized form of the acid. The equilibrium constant would leave out water, of course, because it's a pure liquid. So for the equilibrium of all weak acids, it's the ions over the weak acid concentration. The stronger the acid, the more dissociation and the larger the Ka value will be. A weak acid will have a Ka less than 1. Your hydronium ion concentration will be quite small, meaning the equilibrium will lie to the left, and the dominant form at equilibrium is the non-ionized acid. If you have a strong acid, your equilibrium lies very far to the right. There's no equilibrium constant because essentially you're saying that you have 100% ionization and there is no HA. So mathematically, with a 0 on the bottom, you have a non-defined value. So strong acids have Kas much, much greater than 1. The hydronium ion is equivalent to the original HA because you get 100% ionization. With your weak acids, your hydronium ion is not equivalent to your original acid. You're going to have to solve your x squared over your original molarity and solve for this. So that will be an equilibrium problem. You will not have an equilibrium problem with strong acids. There is no equilibrium to deal with. The reaction essentially goes 100% in the forward direction. So quick review. Strong acids have no Ka values. The equilibrium lies 100% to the right, highly product favored. The hydronium ion will equal the original weak acid concentration. And this means that the A negative is going to be a weaker base than water. We'll discuss this more in class. This is a sort of a tricky concept. For a strong acid to exist, it means that the A negative is able to hold on to that proton. Weak acids have small Kas. Equilibrium lies to the left. You have much, much less hydronium ion than you do have the original concentration. You are less than 1% ionized, and your A negative ion is a stronger base than water. What this means is that the water is going to be able to remove that proton to differing degrees. And when we study and look at what that means, you'll be able to understand if the equilibrium lies to the left, then your A negative is holding on to the proton. If it lies to the right, then the A negative is not able to hold on to that proton. Conjugate acids and bases are just the relationship between the original acid and the form after you lose the proton. The original base and the form after you gain the proton. So acids and their conjugates and bases and their conjugates are always related by a proton. A conjugate base is everything that remains from the acid after the proton is lost, and the conjugate acid is what is formed when the proton is transferred. So conjugates are always on the opposite sides of a chemical reaction. They are never on the same side. This is an acid, this is a base. The acid donates the proton to the base, forming the conjugate acid and leaving the conjugate base. Again, the acid and the base. The acid donates the proton to the base. That's the definition of an acid and a base. The base, okay, when it gets that proton, then forms a conjugate acid, and the acid leaves behind a conjugate base. In the reverse reaction, this is the acid, this is the base. For a base reaction, the water, being the acid, donates the proton, forming the conjugate acid and leaving from the water the conjugate base. Weak acids, okay, have strong conjugate bases, and strong acids have weak conjugate bases. So let's look at this. If you're a weak acid, okay, you're holding on to your proton, that means that your conjugate base is weaker than water. It's not able to remove that proton. A strong acid loses its proton, therefore it forms a conjugate base that is weak. Again, these are concepts we'll definitely have to practice on more in class. You need to make sure that you understand these weak conjugates are simply weaker than or stronger than water. We know that water is amphoteric, meaning it can act like an acid or base. So two water molecules, one will be the acid, one will be the base. A proton will be transferred, forming the hydronium ion and leaving the hydroxide ion. In a neutral solution, there's an equilibrium between the water and the hydrogen and hydroxide ions, and they are also equivalent to each other. In neutral water, the hydrogen ion and hydroxide ion are 1 × 10 to the -7 moles per liter. There's a Kw, or an equilibrium constant, for water. It's called the ion product constant because you basically are multiplying the ions, okay, that are in water. So ion product constant is called Kw, and since each of these values is 1 × 10 to the -7, the Kw of water is always at 25 degrees Celsius, 1 × 10 to the -14. Kw is constant in every aqueous solution at 25 degrees Celsius. So if you know one value, you can find the other. If you know that the hydronium ion concentration is 4.5 × 10 to the -5, you can use the fact that the product of the two ions would be 1 × 10 to the -14, and you can algebraically solve for the hydroxide ion concentration. You can always find the H+ or OH- by using the Kw expression. There are other ways, and often people forget that this is a pretty simple and basic way of finding the remaining ion concentration. Remember, in pure water, you have equal concentrations of hydronium and hydroxide. As you increase the H+, the OH- goes down because the product has to remain 1 × 10 to the -14. In a basic solution, your OH negative is greater than the H plus, so as the OH goes up, the H plus goes down in order to keep the ion product constant. The mathematical relationship between concentration of hydrogen ion and pH is the negative log. Again, molarity of the hydronium ion. Negative log is a function that P means negative log. pH means negative log of H plus. You will later have pKa's and pKb's. P simply means negative log of. It's a log function. The pH and pOH relationships need to be known very well. You need to make sure that you know what values and be able to put them into your calculator quickly. In a neutral solution, these are equivalent. In a neutral solution at 25 degrees Celsius, the Kw is 1 times 10 to the negative 14. The Kw is equivalent to the Ka of the acid times the Kb of the base. pOH would be negative log of the OH concentration, while pH is the negative log of the H plus. The antilog of the negative pOH and negative pH will give you back your concentrations, and pH plus pOH will always be 14. So make sure you memorize these relationships. They're going to be used throughout the next several chapters.